Um, Thanks. Okay, so as usual, I'll recap a little bit and then move on to something that flows from this a little bit. I thought about a new topic, but maybe not. Maybe we'll just continue a little bit with what we have. But I thought I'd start a little bit by trying to show you some of these things. So we talked about this Lamé problem, right? And the actual experimental implementation of this is you take an annulus, you float it on water, you control the tension inside and outside. And I just wanted to show you that this is not a fiction, and these things can actually be relatively straightforwardly implemented. So we brought a few toys to show you. Of course, experiments never work in public. So we'll see how this goes. This is here courtesy Ganga Prasad, who's sitting at the back. Ganga's an ICTS student, and we work together. So what he's done is he's made some rubber bands, if you like, but these are fairly stretchy things. And let's see if we can show you what we have here. So he has one of these things. He's given me a couple of these things. There's one floating in the water. What distinguishes this from standard rubber band is you'll see it's a bit thinner. Can you see it? You can, sort of? That's really dark. Yeah. It's okay for you? Okay. So this is a regular old rubber band, except that it's a much softer modulus material. And it's floating on water. Okay, that's just water it's floating on. Okay? And what you have now is a situation where it feels the tension of the water from both sides. Okay? So the line tension here is water, the air-water surface tension, and here is the air-water surface tension. We don't have an annulus for you, okay? But what I'm going to do is now add a little bit of soap to one side, and you need zoomed in much more? That's about it. What's the problem? You can't see? Excuse me? Are you all right? Okay, good. Complain when you can't see, huh? So what the idea is now is to add a little bit of just that. Oh, you can take a picture, please. Yeah, please enjoy. Oh, you want brightness? Oh, thank you so much. Okay. Actually, don't worry. You're going to be standing there all the time. Don't worry. Yeah, it's a problem for you. So the idea is to add a little bit of soap here. Right? And you can, that's fine, thank you. You can guess what happens there? So the soap will spread out, and what happens then? That's right, so I put a drop of soap there, and the soap will occupy the surface completely. And it does what to the surface tension? It lowers the surface tension, right? So you have, hopefully, we'll see what's going on, but hopefully you will have the lame situation. That's to say, bigger on the outside than the inside. It instantly buckles, right? So you can try this at home. It doesn't matter. The surface diffusion is pretty fast. It'll go uniformly on the surface pretty quickly. Thermodynamics drives this. It's all over the surface pretty soon. The problem with this experiment is if we sit and watch it for a long time, this thing is going to open again because the soap can swim through the substrate. This is not a barrier. This is a little elastomer. It's like a PDMS type of material. But you can, any sufficiently floppy thing. Don't use rubber band, but you can do it with, like these sport bands people wear. That's a softer material. You can cut through one of those and do it. Not me, but there are people who do, right? There's people who wear things saying that's just a commercial liquid detergent. Okay. So, of course, in the experiment, you want to ensure that the surface tension stays fixed. So what you do is you put something in the fluid so that the soap molecule doesn't want to swim up through the barrier. Right now, after a while, what's going to happen is the surface tension in here is going to equalize to the surface tension here, because after a while, it'll swim through the bulk. It becomes homogeneous on the surface very quickly. You can use this as a tunable knob. If you put very little over there, you can use this as a tunable knob because what you can do is, once you have a fixed amount of soap on the surface, you can start compressing that. So have you heard of these things called Langmuir troughs? You can control the surface tension. So here's the idea. You have something like this, and here's a fluid surface. You put a fixed amount of soap here. Okay, then you start moving this barrier. So you start changing the density of the surface. So in those experiments, and in people, there is a tunable knob. This T out is a completely tunable knob. So we'll try it one other way. So the problem with any oil, soap, any of these surface molecules, a tiny amount is enough to do it because they all live at the surface. They'll migrate to the surface very quickly. So a small amount of dirt is enough to ruin this. So we have to change glasses of water now. That thing is soapy forever and forever. Excuse me. So what I'm going to do is, that thing is soap, both things are soapy. I'm going to now add, shoot. This is the old thing, right? Never let your advisor do an experiment. I'm going to take another one of these. Sorry, Ganga, I spilled your soap. This is what it is, reasonably circular. What I'm going to now do is add what remains of the soap that I didn't spill to the inside. And now you can easily guess what's going to happen. That's a real circle now. You can see it immediately, you know. It didn't start off life as a perfect circle like most rubber bands. As soon as you add it, the pressure on the inside is now being tugged uniformly on the outside. You made some other toys, right? I'm going to show you your other toys later. Is that okay? Okay. So that's how these things are done. They're relatively straightforward to do. They're hard to do cleanly. And with the very bendable films, they're tricky to do because those are, you know, they're this size, but tens of nanometers thick. So dealing with them is a little bit delicate. Ganga, I'm going to show your other stuff later. Thanks. I wanted to come back to where we were. Where we were was we had done what we're going to do today is a quick overview of crumpling. We had left it halfway, and then we talked a little bit more about large deformation situations. Yeah? So you see how this thing goes. All right. So what we talked about for the longest time yesterday was solution to a particular problem. And since we spent a time on it, let me go over it again. But more important, I want to spend more time on what lessons we got out of it. So this was this Lamé problem, which is an example of a simplest two-dimensional situations you can think of. It's axisymmetric problem. And it may remind you of many other wrinkly situations you've seen in your common experience. You must have seen, Sandeep was showing me today, growth patterns of things growing out on a surface. But this is the thing you get when you see, for example, a button on a cushion that's too tight, that kind of thing. But Lamé is simpler because it starts off in plane. So the first thing we recognized is the way you generate compression in this situation is by tension. You're pulling and you're pulling, but you're pulling unequally, and that generates tension. Okay? This confinement is the parameter that tells you how confined you are, and how much compression you're generating is the ratio of those two tensions. Once you generate tension going around in this direction, you need a finite amount of compression to buckle. Right? Just going back to the 1D problem. And that, the parameter that tells you when you're going to buckle, is very much like the 1D problem. It's psi squared times a characteristic force divided by bending modulus. I want to contrast this to the 1D situation where we had one parameter. You know, in 1D. So we solved this problem in the way we solved the 1D situation. First, you solve this problem in the planar state. That's to say, you solve only the plane force balance of the Foppel-von equations. The thing that says that just this one, dj sigma ij plus f. We had no f's in here, equal to 0. You solve this, and you see from that somewhere it gets compression. Okay? And you say, if this thing had 0 bending modulus, that would be the length of the wrinkles. If it has some finite bending modulus, then it takes a little bit extra that depends on this quantity to make it wrinkle. Okay? So you take whatever solutions you got from here, you put them into the normal direction von Karman equation. This is the normal direction von Karman equation, is the one that the b times 4 derivatives minus negative quantity times stress times two derivatives. That balances normal forces. Let me write it schematically again, but this was B times 4 derivatives minus sigma times 2 derivatives equals the normal force. Okay? So you put this solution into this, and you find what, and you say, I'm going to take small amplitude wrinkles, okay, and you get an answer for what the wrinkle number should be. And as I told you, in many situations, that produces the wrong answer. So we did this a different way. We did this in a so-called far from threshold way. You say, look, inside here, where wrinkles are going to emerge, I don't know where wrinkles are going to emerge, but wherever they emerge, let's imagine that the sheet is so bendable that it can take care of all the stress. It can make the stress zero. Okay? You keep the size of this zone where stress is equal to 0 as a variable. Still think about the planar problem and find the size that will minimize the in-plane energy. Okay? Once you find that size, you put this back again in that normal form of the normal direction von Karman equation. Okay? And you get an answer for the number of wrinkles. So the thing that I have in my notes, but which I didn't emphasize enough, is that you remember when we did in 1D, these two things had some differences, but they ended up giving the same sort of scaling. They were square root of compression. This looks very much like that. This answer ends up going as square root of tau minus tau critical. Okay. This answer, which we worked out, but I didn't compare them for you, actually does this. They look completely different. One goes as a square root, one goes linearly. That's why the answers I showed you, they were so different from each other. Okay. So from this, we took away some lessons that I think maybe are more general than the specific problem that we worked on so hard. And that's the fact that when you think about elasticity problems, there is a useful parameter to calculate in addition to determining whether the thing is thin. Okay? This useful parameter is called the bendability. The bendability is something like the length size of the thing squared times whatever force you're playing with. In these problems, it's always surface tension, but this could be from something else, divided by the bending rigidity. Okay? What I pointed out yesterday is that this is the product of a number that's large and a number that's small. So it can be large or small as you please. Okay? You can be a perfectly good thin plate and have a large or a small von Karman number, a large or a small bendability. The consequence is kind of nice. If you have small bendability, it's the bending terms that balance whatever it is that's pushing you out of plane. Okay? This is this regime that you're used to with a paper. Bending rigidity of this is what you're doing your work against. Okay? On the other hand, if this is large, then you can almost forget about you could, as a first pass, set the bending rigidity to 0. Okay? And put it back later as the thing that you will fix as a small perturbation. Okay? It's these in-plane stresses that are going to couple to the out-of-plane geometry that will balance something like this. So this is not exactly the same thing as we're talking, but it's what you see, for example, in a bubble or a drop or a balloon. It's always in-plane stresses that are balancing the difference in pressure. Those are not examples of what we're talking about, but it's that same physics. It's something in the plane that's making it rigid against out-of-plane deformations. So these are really, these represent different limits of plate equations. Both of them are perfectly good plates. Both of them are perfectly good elastic materials, but they have very different physics. There's something else that I thought I should tell you about. Yeah, there is one thing I should have told you about, which again I skated over. What I was trying to tell you is this one was like the expansion we did in the 1D problem, right? The near threshold expansion. And this one was a lot like the elastica that we did in the 1D problem. I want to tell you one thing that I skated over, and that is, why didn't I use inextensibility inside the wrinkle zone rather than using stress equal to 0 inside the wrinkle zone? Right? And the reason is that 1D and 2D are different. Okay? In 1D, these are the same things. You know, sigma yy equal to 0 implies epsilon yy is, you know, one being 0 implies the other being 0. Okay? So free on the other side, there was no strains. So the inextensibility and setting stress equal to 0 were the same thing. Here they are not. Okay? Epsilon theta theta comes from, there are two components to this, right? There's one from sigma theta theta, and there is something from sigma RR. Okay. Setting this thing equal to 0 and setting sigma theta theta equal to 0 are not the same thing. Okay. I can, if this is 0, this is 0 and this is equal to 0 are different choices. And the choice we make is to actually release all the stress. Because the system is buckling, it will just move under the stress. So they're inequivalent choices. In 1D, they're actually exactly the same thing. So that's why we made that choice. Okay, I'm going to go back now to the things we said about wrinkles and crumples, which is where we had moved on to when we left off. Any last thoughts, questions, disagreements? Okay. Where we had left off talking about was we were talking about this one. All right? And I think we had sort of worked out what the geometry of this will be. So this thing is an object that is localized and localizes both, involves both bending and stretching. That's what I had sort of hoped to show you last time. And I hope you're convinced. Did you look at a ridge in your clothing or in anything else? I wanted you to be convinced that this is not a pure bending object, that this thing does have a curvature to it and a finite radius to it. So we showed that relationship. We showed that the radius goes as t to the 1/3. And we showed that this bending and stretching is, there's actually something like a virial theorem, that equipartition theorem that shows that these are, in all these situations, that these are comparable. And most importantly, I think we showed that what you see by eye, that these things are local objects, actually is true and becomes truer and truer as the system becomes thinner. So if you ask, where is the elastic energy stored? So the area of elastic deformation as a fraction of total area is something like And this goes as, you can see that this has a thickness in it. And as thickness goes to 0, it's going to go to 0. So you'll cover vanishingly small fraction of the area. So the other object that you see are these cones. And you can see the cones all by themselves, if you like. Right? You see them at the ends of ridges, but the way you see a cone by itself is... maybe I have a picture of that. Take this piece of paper. May I borrow that? Not planning on using it again. Certainly not after I've... So just do this and you'll get a decone. You'll put a piece of paper over it and push it through with your pen. That's the elementary object. Right, so this is the decone. Okay. It's the way you make a cone out of, this is the way you put groundnuts in a paper, right? Same thing. The D is actually a useful word to talk about. Give me a minute. It's developable, developable, but I'll tell you a little bit. Diamond? Dimension. Oh, okay. No, I don't think it's deep brains. It's a different D. That's a thought that hadn't occurred to me. But thank you for bringing that up. We'll talk about D in a second. Okay. So the point I want you to get about this is the cone is just bent in most places. It's only at its core where there's something going on, where there is stretching also. Okay? And we should talk about that, but mostly there's just bending in most of the area of the cone. So let's try and get some sense of how that goes. Energetics of that. Where shall I make space? I'll make space with all that stuff. Let me write D for developable on the board, then I'll remember to talk about it. That's the worst color, right? I'll come and talk about this in a second, okay? So actually, this one is not a bad thing to figure out. Okay, this is this, and then there's something down here. Okay? So in here, most of here is pure bending. At the core, stretching relaxes bending a bit. So the physics of the core is a lot like the physics of the ridge that we just studied, right? Instead of making an infinitely sharp bend, it gives up a little bit, it stretches, you get that sag in the middle. Okay, which makes it a saddle. Yeah, so this thing will not be a point, it'll be, if you look at this, actually this experimental picture does a very good job. It's something like this, right? So you'll see something there. And that's the point that will be plastically deformed usually. If you make this in a piece of paper, you'll see that thing forever. And you should go and look. Go and look a little bit carefully. You'll find it's not a point, it's a little crescent. Okay? This cone can be opened into a sheet. Yes? This can be opened up and coned again, right? A cone is, as we'll talk about in a minute, a cone is one of the few things you can make out of a sheet. And we'll talk about why that is so. Just make coordinates along this and do what you need to do with the cone. So let's just think about just the bending. So this is in this portion, in the pure bending portion. It's just, you go from the core to the size, and it's just half b times 1 over r squared, and, usual thing, rho d rho 2 pi. And the r is, of course, the r is just, rho sine theta. Okay? And you put that in, you'll get and 2 pi rho sine square theta d rho rc to r, and you get something that is b log r over rc. And this is maybe familiarly uncomfortable feeling. The energy of this object depends on the size of the cutoff at the bottom in a logarithmic way. Yes, so you'd have seen 2D problems with defects that interact in this way in many other places in 2D physics. Okay. So this is sort of this R is not super surprising, but if this is the first time you're seeing one of those down there, you immediately realize why you need a core. There is some argument about exactly what there's calculations for what you do with the crescent effect, and I think the simplest thing is, one thing you can immediately do is do the sort of thing you did for the ridge. You can say whatever the strain is, the strain must balance off against bending times, the characteristic curvature in the sharpest direction. Okay? Unfortunately, unlike the ridge, both of these carry the same size. Okay, so both of them have spread out over the same characteristic area. So extracting the scaling of the size of this is a nastier business, which I won't talk about, but it looks something like this. It goes with system size again. So actually the core is influenced by the size of the system, which is actually a very counterintuitive thing, unlike those other problems that you may have thought about. This bit is not super well experimentally tested, to my understanding. Okay. What I wanted to tell you about next is the following. So we've spent our time collecting many of these. Oh, before I go on, there's another version of the D cone, which is called the E cone. And I don't know what E stands for here, okay? So the E, what do you do to make a real cone? You take a circle, You cut a slice out of it and you close it. To make a D-cone, you keep all 2 pi of the circle, you push it in and it elastically deforms. An E-cone is something that has too much material. So you take a circle, and then I cut an extra wedge here. I cut, 120 degrees more. You put it back in. That's an E-cone. That has similar structure. So on the big scale, it's saddle-like. Okay? And then it has a core somewhere where something has to happen to resolve. But far away from here, it's, you get a lot of places is pure bending. Okay? And this is believed as a beautiful set of experiments from Eran Sharon's group, and now exploited very nicely by one of my colleagues to make nice shapes. It believes that this may be why many flowers and leaves, it's a very simple control that gives them beautiful structure. So as you grow, instead of adding material that's proportional to 2 pi r, so that you can make the next layer, grow more than 2 pi r. Okay? Then you have to go out of plane. So you can get higher and higher harmonics as you go further and further. And all that's controlling, something that's quite complicated structure is a 1-parameter family. All you control is how much growth as a function of R. Okay, and you can get a flower that looks like a trumpet, or you can get a flower that looks like this. So they've done it in synthetic systems, but they've also done it by shutting off growth in genetically modified things. They've shown you can just shut off one thing that controls growth rate as a function of R. That's all you need to control. You don't need to put in by hand theta dependence. You just control the R dependence, and it'll translate into out-of-plane buckling that these things. And these are actually, it's a very nice system. People have done this now in 2 or 3 different ways. You can program how much something will grow, or how much something will swell as a function of space. So you make it dry, then you throw it in water, and it'll make a shape. Because not all of it swells at the same rate, so it doesn't grow isotropically. One thing I told you a lot about in the 1D case was how you go from wrinkles to the localized version, which was folds. The equivalent thing of going in the 2D fold, 2D wrinkle situation to true crumples, that's to say ridges and decones, is still somewhat an open problem, more than somewhat. So I told you about this experiment in which you try to put a flat thing on a sphere and you generate wrinkles. So I can show you what it looks like. I have this from many days ago. It feels like many days to you, probably more. Yeah. I showed you things that look like this. And then as you change the curvature, they look like this. Okay? They start off flat, then they get wrinkles, then they get more wrinkles. I want to follow the story further. I want to say, suppose I make it even more curved, what's going to happen? What happens is this. Many of the wrinkles go away, and some start winning. Okay? They get more and more pronounced, and in the end, this thing stops, the drop stops fighting and says, okay, I'll compromise, I won't be quite spherical. And you get very deep features like these. These have a lot of structure in them. They look sort of beautiful. It's the kind of structure, if you saw naturally, you would think involved a lot of information content. It doesn't. It just involves one thing, which is how curved is this object. So I think a good way of describing the earlier patterns is Fourier modes. At some place you start seeing maybe more than one mode, but these are truly localized. I think this a mode is not a good description, right, anymore, I think. Right, so these are localized things. And, again, you see this in materials often, right? These are analogous to like grain boundaries or scars in a material or other material defects. But they're different, and they're not, this transition from delocalized to localized in 2D is still sort of an open question. Let me skip past all this. Here's another wrinkle to crumple transition. You can see it in ribbons, and maybe this is a good time to show the toy that Ganga made. So what these guys do is they start off with ribbon, pull, and twist, okay? And you first get a ripple state, and then it starts kinking. It'll make very sharp folds. So, is a good one to show? Okay. So what he did was he made two materials that are two of the same material. So he had one strip, and onto it, he stretched it out a bit, and then onto it he stuck another piece of the same thing. Okay? So the metric in both materials, the natural metric, the strain-free metric is different. Okay? So this piece, which is neighboring to this piece, wants to be a different length. Okay? It's an alternative way of going through this route. Okay? So here's, one is stretched and one is happy. One is under compression and the other is happy. So it'll first wrinkle and then it can actually fold up quite a bit. Was the other one more useful to show? Yes? Does the same thing? Okay. So that's flat, and now you start getting it's incompatible with what it wants to be. So you can generate these under many ways, not just external force. You can have some internal incompatibility, internal frustration that it's not happy with. Okay, so we've collected now a whole bunch of these little pieces, folds, wrinkles, crumples, and maybe more complicated objects that we haven't talked about. But what I wanted to tell a little bit in the time we have left is what can you get out of wrinkles and folds and crumples, I want to tell you, I want to give you some qualitative sense that when you have large enough bendability, these things are so cheap to make that they can be used for whatever you want. They can achieve for you fairly non-trivial shapes, and I want to show you some examples of that. But first, I wanted to tell you maybe some general principles on this. So I'm glad you asked about what D meant. D meant developable, and we'll see why that's a useful word. By the way, I don't know what econ means. I think E may extra. I don't know. E is extra, or maybe it's just the next letter in the alphabet from D. Do you know what econ means? Okay. So the thing I wanted to tell you is that's been sort of a hiding at the back of our all our discussions is sort of a basic geometrical principle which I will describe for you in the most horribly informal language, okay? This is a theorem due to Gauss. And this is called by him the Theorema Egregium. That is to say, amongst the theorems he had proven, this is the one he decided was remarkable. And this is kind of a, maybe, once the story is said, it feels very natural. The statement is, so what do we have in let's talk mechanics for a second, and then we'll talk about geometry, and then you'll see how they're related. What we have in a thin object is a separation of spatial lengths. That immediately led, on first day, it led to a separation of energy scales. You want to avoid stretching at all costs. Sometimes you're forced to stretch. Okay? If you can do something by bending, you'll do it rather than doing it by stretching. Okay? Occasionally, in very localized places, you'll do it by stretching. Okay? Now, let's say what he had to say. What he had to say is, if you're trying to look at a transformation of a surface which preserves lengths in the surface, so the lengths of all curves in the surface are preserved. Okay? So, so the word for that is isometric. These are length preserving. If you have an isometric transformation, that's to say you take surface A and turn it into surface B and not change the lengths of curves, then the following, I need to introduce another piece of word, another piece of terminology, which has again been lurking around the background of what we've done, which is a slightly fuller description of curvature. So we've been saying curvature, curvature, curvature as second derivatives. I can erase it because now I'm talking about it. But you realize that you can take second derivatives in two directions, right? Or you can take second derivatives in many directions, right? So say you have a surface and you're taking curvatures along it. This is actually a tensorial object. So let me write this in ugly coordinate-dependent representation as height as a function of xy, as I've been doing. And you construct the curvature tensor, which is two derivatives in this direction, yeah, you take derivatives in all the directions. You realize this is a symmetric tensor. You can turn this around, and you can find places where you can turn this into diagonal form, and you can find places where there's zero curvature in some directions, and curvature in the biggest and the smallest, the eigenvalues are orthogonal to each other. Okay, so these are the two principal curvatures. You think about this on any surface you want. Think of it on a cylinder. One will be this direction, one will be the straight direction. Think on a sphere, it's completely degenerate. You can pick any pair of directions. So there's two invariants of this object, right? There's the trace and there's the determinant. We've talked, this guy has been hanging around in the background when we talk about how we deal with bending terms and how you couple the stress to this curvature term everywhere. So in the energy, what you want to do is, what we've been doing, without being very explicit about it, is we've been coupling bending to, you add up these things. Okay, you say this much energy to bend this way, this much energy to bend that way. Okay? So we've been talking about the trace there. What I'm going to say in a second is the theorem, which is about the other invariant, which is the determinant, right? So the trace is kappa 1 plus kappa 2. And actually, sorry, I'm going to call trace divided by 2. This object is called the mean curvature. The determinant is kappa 1, kappa 2, and this is called the Gaussian curvature. Okay? So, what's the mean curvature of a sphere of radius r? R. And mean Gaussian curvature of sphere of radius r? R squared. Mean curvature of cylinder is just the radius divided by 2. The other, yes? The other direction it's... Okay. How about, what is the Gaussian curvature of a cylinder? 0, cone 0. Okay? So the things that we've been dealing with that you can fold objects into easily from a plane are Gaussian curvature 0. And this is the content of this gentleman's theorem, his remarkable theorem, is that these transformations also preserve Gaussian curvature. I don't think he called it Gaussian curvature, but he called it remarkable. Okay? You see the... So it's easy to change mean curvature. Another way of seeing this is if you can take an object and you can rule straight lines on it, then you're okay, like you can do on a cylinder. So that's what developable means. You can come from a flat surface and develop this without changing any lengths. So you can immediately see that just like the trace is related to the bending energy, the Gaussian curvature, if there is if you develop Gaussian curvature, it means you have to change lengths. So Gaussian curvature involves changing in-plane things. So either you need shear or compression or tension inside the plane. Okay? So changing Gaussian curvature of an object involves lots of strain. Okay? So this couples to that second term in the Foppel-von-Karman equation, the one where you have... Okay? So what's that got to do with anything? What that's got to do with anything is, if you start with something flat and you want to turn it into a curved shape, you have to do something. So you have to somehow make this object develop you have to have some place for it to develop curvature. And there are two primary routes that people use to try and do this. One has been known for a while, and I think mathematicians have developed some very beautiful results, and I think physicists are right there in this game also. That's to say you put singularities in there. So the word you attack is, I didn't say smooth. So smooth. I'm not putting all the good qualifiers here, smooth, local. So the way you can do it is you can tear the material, obviously, and you can make any shape you want. But a fold or a ridge is such a thing. Okay? It's a singular place. Okay? And I think this is a pretty recent paper, which is actually, for me, quite a remarkable thing. This is pure origami. It started with a flat sheet. And you can make something with positive Gaussian curvature. This is negative Gaussian curvature. And both. Okay? Which is quite nice. And I think there's now a beginning of a realization that you can make very complex shapes, not necessarily with defects, but also with smooth objects like wrinkles. So this is an old one. If you stand at the top of a table tennis ball and you want to displace it inwards, okay? Say you want this point to be here, you have to change Gaussian curvature at many places. The one simple way to do it is to just take this piece and just do this. Okay. Flip the cap. That involves either surgery or lots of plastic distortion there, okay, around the ring. But otherwise it keeps lengths everywhere, no? Apart from that place, it's purely isometric. And that's the idea of origami. You can do this. So here is a relatively new construction that says, okay, you want me to come here. There's a way to do it with wrinkles, with smooth distortions. If you have enough, that looks like the top of an apple. You can achieve that shape from the sphere shape with very small distortion. And in fact, in the limit where external tension is small and bendability is very small, this is a very good isometric deformation. You put the wasted space somewhere else in the other dimension outside the surface, and this is really very low cost deformation. I want to show you some examples of what happens at intermediate bendability and high bendability. So I showed you examples of something you're trying to make it live on top of a sphere. We have a geometric reason now to back up our energetic reason why it's kind of difficult. I want to show you now folks who try to take this thing and now let's say, okay, let's try to wrap the whole object. So there was a very cute paper a few years ago entitled Capillary Origami. It's not origami at all, but it's very nice. So what they do is they take a soft material, okay, roughly like this stuff. In fact, we learned how to make these things from them. And what you do is you put a drop of water on it, like on this. The water wets the triangle, okay, the whole thing, and then the water starts drying up, starts evaporating. So it picks up the arms of the triangle and it closes it. You get a little pyramid here. Okay. Start with the Latin cross, you'll get a box. Start with this floral pattern, you'll get something that approximates a closed flower. Okay. It's very nice. You see what they've done? They've completely got around Gauss. These are nearly fully developable shapes. Yes. I should have brought a video. But they put a drop of water on this flexible sheet. It'll wet the sheet, and it'll make a drop on top. Then it starts drying. So, you know, the surface tension starts picking it up and up and up, and it closes. And then after a while, when this water is dried up, it falls open again. Of course, if you want, you can do some chemistry to catch it at this moment and seal it. After, yes, completely reversible. And you can see they've chosen a clever design so that everywhere it's developable, now that we know that word. Right? There's only curvature in one direction. It's very rarely bending in both directions. Okay? This is now that you know these, oh, I should have put it out here. This is, you know, thickness about 50 micrometers. So this is like a piece of paper thickness, or a thick piece of paper, and it's a few millimeters across. And what's going on here is really in the small bendability limit. The bending of this balances the torque produced by the thing that's pulling it. Okay? Now I want to show you what happens when things are much thinner. Okay. So you see how you've got around curvature problems, right? This object looks overall curved, but locally there's no Gaussian curvature anywhere. There's only mean curvature. Okay, so I'm going to try for something thinner, and you know why, right? You know we're going to go into a different regime where defects cost less. Okay, so what I have here is a movie. I'll start it in a second, but let me tell you what's here. Here's a drop of water. It's sitting on a syringe. On top of is a little circular raft of plastic. Okay? And, you know, this bit is like the experiment that we saw some versions of earlier. Right? You're trying to put something round on the North Pole. But what we're going to do here is suck out some of that water. Okay? So all kinds of wrinkles are becoming crumples, etc., etc. Okay, now you keep going beyond the point where I stopped. I told you we don't even understand what's going on here, right? Once we've gone past the wrinkle phase, we don't really understand. But take it all out. And there you are. You have a nice little sealed package. Okay? And that's the package shape it chooses by itself. All right? Same from above. Above, the view will look more familiar to you. You start getting wrinkles. The wrinkles start getting quite deep. Maybe you shouldn't be calling them wrinkles anymore. Okay? And now you can't see the edge of the thing. It's gone the other side. And it's made some shape. Okay? And it's done. All right? It's made a... Now, I told you, right? I told you we can't even understand... so a couple of things happened, right? We're at this stage already, we can't understand very much. But then after that, it turns polygonal, then goes from, I don't know, 7-sided to 5-sided to... And you get something like this, okay? So this is a nasty problem to think about. You have wrinkles, folds, crumples, everything, and they're all on highly curved surfaces, not near, not the gentle, small slope kind of thing I was telling you about. So there's, we thought there was little or no hope of any understanding. But there's a big clue. The clue is you do this with materials of different thickness. So this one is under 30 nanometers, that's about 250 nanometers. And the details look different. Like here, the wrinkles look very coarse, there the wrinkles are very fine. But the end results look the same. Okay? And now you know that when going from here to here, we've gone a factor of 9 in thickness. That's 9 cubed in bending modulus. Okay, so this is 1,000 times stiffer than that. Okay? And nothing really is changed about the picture. So what's up? So the lesson is that maybe for this, mechanics is unimportant. And indeed, here's bendability coming back. It turns out, this is the return of Vincent d'Emery. You can describe all those shapes with just one simple equation, and I'll tell you how it boils down to bendability again. Let's say you're given this amount of material to wrap a drop of this volume. Okay? And let's say the only thing the drop is trying to do is the sheet is trying to do is cover as much as it can. Okay? That's to say, leave as little area exposed. And let's say what it can do is material points can never stretch because stretching is expensive, but they can come together in some unspecified way. They can either make wrinkles or crumples or whatever they like. In 3D space, they can come close to each other, but they can never go further away than they were initially. Okay, so no stretching, but free compression. It turns out this is a very good description. This is a description with pure geometry. The material parameters don't matter at all if this description is right. Right? The energy is got some material parameter in, which is the surface tension of the surface. But that could be 10 or 5, it wouldn't change the physics, right? That's just a prefactor. Okay? So really where this is this says bending energy is very much less than stretching energy. And in between, it's very much less than some other energy in the problem. And in this case, that energy is surface tension. You can see this is exactly, this inequality is just high bendability. This inequality is just small strain. Okay? So if these are all well separated, it's a completely different regime than the capillary origami which I showed you, where bending approximately balances this. So the physics changed quite a bit. Now you're allowed to do any kind of compression you like. So I won't belabor it too much, but the description is very good, gets the shape of this thing correct. It's not a sphere almost very soon, even before it's well before it's wrapped. It looks more like a parachute shape. Actually, there's a calculation from Taylor ages ago that's relevant for this. The wrapped shape is predicted very nicely by this. And in fact, we used to see this very often. And the calculation showed that this shape, which we saw more rarely, is actually lower energy. It's more efficient. And I think it's not a coincidence that you get a lot of food shapes in this. You're trying to do the same thing as food. You have a certain surface area of dough, which cannot be made too much thinner. And you have a certain amount of filling. You want to maximize the amount of filling. And that's why, and you want to close the surface. So these are some common shapes you can get. And I don't know that we don't have a proof that this is the best shape that is possible to get. But it seems to be that this is a very good shape. You can play around a little bit with largest volume that you can enclose with a given surface area with one additional rule. You may compress as much as you like, but you may not stretch. Okay? So it's a different problem. Mathematicians have thought a little bit about this, but it's sort of a relatively new maths problem also. And they've realized, so the one thing that one very, very nice result is, so suppose you have, I hope I don't get this wrong. So suppose you have a cube, sorry. If you allow compression of the material, you can increase the volume enclosed in the cube. Just by cutting and pasting it. It looks like all surfaces are flat. Things are being used very well. Space is being used very well, but you can actually do a little bit better. I think I got that right. Okay. Okay, so you can start off and get other shapes as well. Okay. We started with a circle, and a circle is a very difficult problem for a material to solve, right? Gives you no easy direction of folding. It says, you please find out what's best. If you give it a hint, like this will close into, this is the net for a tetrahedron, that's also a net for a tetrahedron. You don't need to put the lines, you don't need to put dotted lines, you don't need to do origami. It does the origami by itself. You don't have to fold here and here. That folds into this cube. This thing folds into a slightly lousy looking cube, but then I won't discuss too much, but you can get other materials. But the general point is really the third point I wanted to say. If you have thin enough materials, thin defined in that way, then you have a lot of deformations that you wouldn't think are useful. These are only compressive things, but you can actually achieve a huge variety of shape, smooth shape. Okay, so where we started off with was trying to look at all these things in some place. And we've gotten some distance there. There were two other topics that came up that I had hoped I could do, but it's not going to happen. Rather than launch into a completely new topic on the last day, I thought we'll follow this path a little bit further. The two topics, one was just to justify my appearance at a stat physics school, was how this plays out when these are thermally excited. And this is a kind of an interesting and now a moving field again. So this was a field that came up first in the mid-80s. So the question is, if you have a polymer membrane, which is, or any 2D membrane, and you sit, is there a low temperature smooth phase, and does it go into a rough at finite temperature? Does it get thermally populated enough? Is there a sharp transition between a low temperature smooth phase and a higher temperature roughened phase? So there's a whole spate of calculations then. Didn't go outside the world of theory. And at some point it got dropped. There's a huge revival of that kind of physics now, because there are so many nice new 2D materials. In particular, there's a lot of interesting debate around graphene. Graphene and other truly molecularly thin materials, we are close to molecularly thin sometimes when you go to 10 nanometers, but this is not molecules, not single molecule by any means. This is really continuum. But those materials, the first relation I told you is in continuum, bending goes as E times thickness cubed, stretching goes as E times thickness. That's not true for a graphene sheet. The physics of stretching those rings is quite different from the physics of bending them. You can't integrate over the height of this thing and get an answer out. So these things are two independent numbers. And measuring the bending modulus of graphene and of the other new 2D materials has proved kind of interesting and frustrating. And it turns out that graphene is much stiffer to bending than would be predicted from ab initio chemistry calculations. And the consensus is we should go back to these calculations made in the 80s and 90s. Nelson, Pierre Ledussal, and Leo Radziowski and co. I'm missing people, I'm sure. And revisit those. So the thought is that a sheet like this has thermally excited modes on it. And you can already tell this, right? This is floppy. But now if you want to curve it the other way, not so floppy. And we saw, well, on the board I erased the geometrical reason why. It's you can't generate Gaussian curvature very easily. You have to stretch. Okay? So suppose you have a thermal population of waves or scars or something on this, this thing suddenly becomes stiff. Right? It can bear weight. So that's the set of things that I might have done. So people are revisiting these calculations in new ways of thin shells and thin sheets with thermally populated wrinkles on them. So you have out-of-plane phonons. A little bit surprisingly, people haven't yet put in sharp things in them. People haven't put in folds and ridges into these calculations. But maybe that's something you could do now that you know the energetics of ridges. You know how to put them onto a sheet. The second thing that I wanted to spend a few minutes on, but probably shouldn't, is somebody raised this question, a couple of people raised this question with me. What's the contrast with fluid membranes? So there are solid membranes in our natural world everywhere. But if you look at a sort of meso level in biology particularly, most membranes are fluid. And there are differences from this, obviously. In fluid too, you pay cost for area. There's a surface energy for area. You can pay cost for bending. You don't pay cost for in-plane shear. Right? This thing is fluid. So I had that's another thing I would have gone into if I had gone sufficiently fast in the first couple of days. But that's another. Hopefully, if you need to look at that literature, some of this will look familiar at least. And there's a lot of that literature, by the way. Fluctuating fluid membranes are much more heavily studied. Okay, so we are close to the end. Let me say a few thank yous. One is to all of you sitting patiently. And we'll soon hear your life histories. I think second is to a bunch of students, postdocs, and collaborators who have sort of educated me on this. But finally, we should thank Abhishek and Sanjib. I run a summer school in soft matter every year for the last many years with other colleagues. And I must say, we run a one-week school. I'm exhausted at the end of that week. They've been going for 2.5 weeks, so I really appreciate it. And also, I must say, I think I speak safely on behalf of Arul and David. We were talking the other day, and Sandeep also, and maybe Peter Young was also there. But things run smoothly here. And thank you for that. I mean, it's everyone, the admin staff, the folks up there, the ladies who clean the boards, coffee appears, tea appears. So it's from all of us. Oh, by the way, notes are halfway through and I'll have them all up there, including references soon. Okay.
Any questions? I had some question, but I forget now.
That's okay.
Okay, so again, let's thank Narayanan again, and especially because this was like he showed us real experiments, which is really important. And hopefully we'll have him again a few years giving, talking about fluctuations. And let's also thank all the other lecturers.